Hello everyone. I hope you are having a wonderful day. We are going to focus on the torsion test today. The reason I'm uploading this video is because we are going to have a torsion test this week. I'm sorry. So torsion test is going to be this week. Okay. And I just want to stay ahead of the labs because of the fact that we had to do the lab on a Thursday, the tensile test on a Thursday. We are 1 week behind, so I have to upload this lecture, and then on Thursday we'll get to in the face-to-face class we get to the discussion about the lab that is going to be next week, essentially. Okay, but the discussion for today is all about torsion. That's what we are going to discuss, and the outline for today's torsion discussion is the first part of the lecture is not about torsion. We are going to talk about ASTM standards. Specifically for bending, we're going to watch some YouTube videos of these standards for bending. And then we will talk about torsion in aerospace a little bit, which we have already. If you recall, we have talked about torsion boxes before in the previous lecture. And then we will talk about the theory of torsion. We will develop how to relate the angle of twist to your torque. And then we will discuss a test we are going to run in the lab. Okay. So ASTM stands for American Society of Testing and Materials, right? It is an international standards organization that develops and publishes voluntary consensus technical standards for a wide range of materials, products, and systems. So essentially what you have here is a set of standards for all of the tests, bending test, tensile test, all of those things. Like the dog bone samples we used for the tensile test was manufactured based on one of the ASTM standards. So, and their goal is to make all of the tests done everywhere in the world uniform, which will help you compare the results of each test with each other, right? So that's the goal of a standardization in general. And ASTM as a company aims to do that. They have been around for a while. They have been for a long while. And they have thousands or definitely hundreds of standards for each specific mechanical or material test, right? A couple of examples for the bend test, which is and these are all available. I have a copy of all of these standards, so if you were interested in reading about those and seeing a real standard, they usually look like a paper, a journal paper. Yeah, so if you were interested, just reach out to me. I can share it with you guys, or I can upload it on Blackboard if you were willing to read more about the standards. But the first standards we want to introduce is the ASTM B82018-18, which is the standard test method for bend test for determining the formability of copper and copper alloy strip. Second one is D6272-17, a standard test method for flexural properties of unreinforced and reinforced plastics and electrical insulating materials by 4-point bending. And so they go into a lot of detail actually about each test. Yeah. They discuss the loading situation. They discuss the type of test you want to run, which in our case is the bending, right? They discuss what you want to calculate with this specific test. They actually discuss all the sizes you want to have, all the like material you can use. They discuss every single detail you may want to use in a specific test. I don't want to read over all of these tests. You can always come back and see what each of these standards do or supposed to guide you through, right? Yeah, we have a lot of bending tests. I'm just going to focus specifically on a couple of them. The first one is ASTM D790. What we are going to do as far as these standards go is we are just going to go over a summary of what these standards do, right? This is a bending test standard that tests the bending, measures the deflection essentially on a for unreinforced and reinforced plastics and electrical insulating materials. ASTM D790 is used to measure the flexural strength and flexural modulus of unreinforced and reinforced plastic, as I said, including Hall modulus composites and electrical insulating materials. What you see here is the standard roller. Roller for this specific type of bending test. These standards include detailed specification on the recommended bend fixture for this type of testing as listed here. The bend fixture must be the rectangular specimen is loaded by a loading nose midway between the supports. So which essentially means that we have a 3-point bending or 3-point loading, which you have already seen in the lab. Right. The recommended support span to depth ratio per ASTM D790 is 16:1. A larger ratio than 16:1 may be necessary for laminated thermosetting materials and materials used for electrical installation. The recommended loading nodes and supports are cylindrical rollers, as you saw in the previous picture. In the previous slide, actually, in the previous slide, the default radius of the loading nodes and supports are 5 plus minus 0.1 millimeters, or in inches is going to be 0.197 plus minus 0.004 inches. As you can see, they go into a lot of detail. They discuss what should happen if you don't use the defined radius. And they talk about the maximum radius of the loading nose. So these are very, very detailed things. So they essentially want to create these standards. They want to make them as detailed as possible so you can always compare the results of a test that is done based on the ASTM D790 to wherever. And it makes manufacturing the samples easier. It makes a lot of things easier. Standardization is always a good idea. Okay. The next test is another that we want to discuss a little in detail is the ASTM C1609. It's again for a bending test of a fiber reinforced concrete beam. So it is mostly used for civil engineering applications. ASTM C1609 is used to measure the flexural performance of fiber reinforced concrete beams. The purpose of this standard is not only to determine the peak strength of the concrete, but also to find the residual strength of the fiber after the first crack appears, which is a very important element in concrete analysis in general. For this reason, the test extends past the initial peak. Okay. The standard also specifies that the test must be performed in a servo control at a very slow net deflection rates. Net deflection is the average of two displacement sensors placed on either side of a specimen. You have the recommended size of the specimen. You have to have two loading noses to apply load to the top of the beam, and we have all of the sizings and everything here listed here, so you can always go through them. And here we have a picture of this test. As you can see, the loads are going to be applied here and here, right? And we have the support system right here, these two at the two ends. So this is actually a 4-point bending test, right? We definitely could do the 4-point test, and actually that was one of the things I wanted to do in the lab, but since we had to change the schedule, you guys couldn't get to doing the 4-point bending test. But yeah, you can see, we will definitely see a YouTube video about the 4-point bending. And here, these are the devices which we have, one on this side and another on the other side of the concrete beam. These are the devices that measure your deflection. Okay. So yeah, let's go ahead and watch this YouTube video. I'm sorry. So yes. I'm not sure if you have the audio. If you hear the audio, you're supposed to be hearing the audio in my recording. So the guy here is essentially explaining what he wants to do, but we already know what he wants to do. He wants to do the ASTM C1609 testing with this device. You can see you have the two supports here and here, and this is actually your load cell is connected to this two loading noses, yeah, two loading noses, and we are going to perform the bending test. Let me actually go a little further ahead. So they have loaded the concrete, and yeah, they have loaded the concrete here, and you have the transducer that will measure the displacement with you. Okay, so you can see the progression of load versus deflection when you run the experiment using this machine. Of course, the test you're gonna run in the lab is all uh, analog. There is no digital component. There's a computer component to it. So you have to like read all of the data by hand, record all of the data by hand in a table, as it is pointed out in the manual. Okay. So what you see here is that is actually the load after the first crack has appeared, right? Okay. So that's it. And let me go back to the PowerPoint here. Yeah. But ASTM is not the only company in the world that does uh, the standardization of mechanical and material testing. Another company that does this, another group, I would say, that does this is the European Standard Commission, which gives out this EN. Now, whenever you see this a standard that starts with EN, it's from the European Standard Commission, right? So UN has the same standards. They're similar to ASTM standards, but very small differences. For example, this EN 14 14651 is pretty similar to ASTM C1609, but the differences in the test specimen size. The other difference is that it is a 3-point bending instead of a 4-point bending, so one loading nose instead of two loading nose. And the distance between supports is going to be different. The loading nose material is going to be different, and EN that test requires just one transducer. And we actually have another YouTube video. Yeah. That is going to discuss this YouTube video is going to discuss the EN 1469, and you're going to see they are pretty actually similar. Okay, so you can see this is the part when you put the legs of a displacement transducer, and as I mentioned, we only need one transducer, so we don't take the average between the deflection that is given to us through the two different transducers. So the crack is becoming visible to our eyes. I hope the video quality is good enough for you guys to see this crack that is appearing. So you saw the crack propagation here, and at some point the concrete fell. Something that you have to keep in mind is that here the deflection we are measuring in this standard is a little different from the deflection we measured in the ASTM standard. But yeah, so let's go back to the lecture. So yeah, that was an introduction to the two standards EN and ASTM. That ASTM 16C1609. I forgot the EN number. EN 14651. That related to the testing of uh, concrete. But we also have other testings, other ASTM standards for testing of metals, testing of composite and plastics. For example, the ASTM D2344 is a shear testing of a polymer matrix composite material. It is used to determine the short beam strength of high modulus fiber reinforced composite materials. But you may want to ask, what is the short beam strength? Short beam strength refers to the shear stress developed as the specimen midplane at failure. Okay. The beam specimen is loaded in 3-point bending using the specific bend fixtures described in the standard. And we are going to have, so based on what we just said, we are going to have one loading nose and we are going to have the support. But the supports are specific supports, are not regular supports. Let's actually watch another YouTube video for this bending as well. The quality of the sound is in this video is terrible, so I'm just gonna mute the video. As you can see, you have to make sure all of the measurements are following the standards, the ASTM standard. Okay, and then it's just a regular 3-point bending, but with a specific with a very specific support system. I'm not sure if, so we just had the failure, and that's the point you are really interested in. You can see the failure effects here. So you can have different bending fixtures. You can see a host of different fixtures we have here, and all of these standards covered. But this was supposed to be an introduction to ASTM standard and the process of creating these standards as well. And yeah, for you guys. So if you were doing a test somewhere for a company or whatever, they're doing a tensile test, doing a fatigue test, doing whatever type of test you're doing, you just have to make sure that you follow a specific standard based on what you need, of course. But this is you have to pay for the standards to be able to purchase them, each of the standards. But I have some of them. I have the PDF version of some of them. I can share them on Blackboard. I cannot just so you can use them for educational purposes, of course. But yeah. So let's move on. Let's move on to the torsion theory, which is the topic of the experiment we are going to have on Tuesday. I assume it's going to be Tuesday, the 7th October. Tuesday, October 6th. Right. Yeah, we're going to have that experiment, the torsion experiment, on October 6th. But we have to cover the theory first before going into the lab. And that's the reason behind the online lecture, right? So let's cover the theory first. We are interested when doing a torsion analysis in general. We are interested in stresses and strains of circular shafts subjected to twisting couples or torques, right? So in the mechanism you see on the left-hand side of your screen, I'm sorry. What happened? Okay, sorry, we're back. So in the mechanism you see on the left-hand side of your screen, what is happening here is that the turbine is exerting a torque on the shaft, and this shaft here transmits the torque to the generator, and generator of course creates an equal and opposite torque, T prime. Okay, but we are interested in measuring the angle of twist that is caused in the shaft by applying this torque. So that's the whole purpose of this lecture, the torsion analysis in general, and eventually you wanna find the failure point at which the torque you need to break, or the torque you need for your shaft to break, right? So to start the theoretical analysis, you want to find the net of internal shearing stresses, which is an internal torque, and it is equal and opposite to the applied torque. So it is going to be equal to the integral of rho df, and df is a small element of force here, and which is going to be equal to your shearing stress multiplied by the small element of area, as you can see right here. And always keep in mind that rho in our course usually refers to, when you're dealing with mechanical testing, it refers to the radius, but when we are dealing with the fluid testing, it always refers to density. So you always have to be mindful of that, not to make any mistakes. All right. Although the net torque due to the shearing stresses is known, the distribution of stress is not known, right? And the distribution of shearing stress is statically indeterminate. We must consider the shaft deformations to be able to find the solution to the problem at hand. And unlike the normal stresses due to axial load, the distribution of shearing stresses due to torsional loads cannot be assumed uniform. Okay, let's try to find the shaft deformation then, or the angle of twist in general. Let's look at a very small element of this shaft, and you have the axis of shaft here. We are looking at a very small stress element of the shaft. We want to find the torque applied, the shearing stress in that very small element. And torque applied to the shaft produces the shearing stress on the faces perpendicular to the axis, of course. So the conditions of equilibrium require the existence of equal stresses on the faces of the two planes containing the axis of the shaft. Okay. The existence of axial shear components is demonstrated by considering a shaft made up of axial slats. So you can see the effects of shear stress when applying a torque here, right? The slats slide with respect to each other when equal and opposite torques are applied to the end of the shaft, right? But how can we find this angle of twist, how much the deformation is essentially that represent the angle of twist represent your deformation, and that's why we want to find it. So from the observation you can have here, you can see that the angle of twist is actually is going to be related to the torque you are applying, which is something that you can figure out on your own. If you apply more force, more torque on a shaft, it will twist a little more, and it's also definitely dependent on the length of the beam. So when subjected to torsion, every cross section, and you have to keep that in mind, that when subjected to torsion, every cross section of a circular shaft remains plane and undistorted. So this is a very important assumption we are making that is going to help us with the analysis, right? Cross section for the hollow and solid circular shafts remain plane and undistorted because a circular shaft is axis symmetric, which essentially means that if you are not dealing with a circular shaft, you are going to have a distortion. You cannot assume that the cross section of a non-circular shaft is going to remain plane and undistorted. As it is obvious from the two pictures, you can see if you apply this torque, you are going to have a planar circle here, but when you apply the torque to a square shaft, there's obvious distortion here. You can see that. So we cannot make this assumption for a square shaft, right? So to further the analysis, consider an interior section of a shaft. As the rotational load is applied, an element on the interior circuit deforms into a rhombus. As you can see, from a square to a rhombus, right? Since the ends of the element remain planar, the shear strain is going to be equal to the angle of twist. Okay, so this is where the planar assumption help us, right? We can relate the shear strain to the angle of twist, which represents the formation of the angle, which is going to help us to be able to solve the problem we were having with the statically indeterminate beam, right? So L, you can see this arc length actually here. This arc length here is going to be equal. It doesn't matter which perspective you use to calculate the length. The length is always the same, right? It's the same arc length. So if you use point O as the center of your coordinate system, this arc length is going to be rho, which is your radius multiplied by phi, right? But if you use point B as the center of your coordinate system, the arc length is going to be your gamma, which is your shear strain, multiplied by this radius, which is the length of the beam. So the two are going to be equal, and your gamma eventually will end up being equals to rho phi, your angle of twist, divided by L. We can see that your maximum shear strain is going to happen at the surface of the beam, right? Because it is of course related to the C and L, your shearing stress, as you can see, right? And when you increase the C, when you increase the circumference, you are increasing that arc length, which is going to tell us that we are going to get the maximum shearing strain. So your maximum shearing strain is going to be C phi, which is your circumference of the beam, over L. So we can relate the shearing strain to the maximum shearing strain using this analysis. As you can see, there's a linear relationship that goes from 0, where rho is 0, to the gamma maximum, where rho is equals to circumference. So your distribution is going to look like this, the distribution of shearing stress. But how can we find the shearing stress? Pretty easy. We want to use the Hooke's law. So you multiply both sides of this equation right here by the shear modulus, G. So we're going to have G omega is going to be equal G gamma is going to be equal to rho over C, G gamma of max, and then based on the Hooke's law, we know that your shearing stress is equals to G multiplied by the shearing stress. So your tau, we are going to have the distribution of tau or shearing stress. Your tau is going to be equal to rho over C, tau of max, right? Which help us to conclude that the shearing stress varies linearly with the radial position in the section. But then the question is, how can we relate this to the torque? If you recall from our previous force and moment analysis, we know that the sum of the moments from the internal stress distribution is going to be equal to the torque on the shaft at the section. So your torque is going to be equal to the integral of rho T dA, right? We can replace tau with this equation we have right here. Tau of max is going to be constant for a specific t, right? C is always constant, so we can take that out of the integral, and your integral is going to be t equals to tau of max integral of rho squared dA, and your rho squared dA is the polar second moment of area or polar moment of inertia, or J, right? So we can say that we have the results for the elastic torsion. Tau of max is going to be, we have the equations for the elastic torsion. Tau of max is going to be Tc over J, and tau in general is going to be equal to T rho over J. Okay. But how can we calculate J, the second moment of inertia? In general, you have to take this integral, of course. But in our experiments, we are only going to use a circular shaft and a hollow shaft, right? A hollow. For these two, the polar moment of inertia can be calculated using these two equations. So essentially, you have to have the inner diameter and the outer diameter for the hollow cylinder or the hollow shaft, and you have to have the diameter for the regular shaft. Okay. But how are the normal stresses? Do we have any normal stresses when applying a torque to the shaft, right? Yes, we do have. We definitely are going to have normal stresses. It depends on the element you are going to use when doing the analysis. If your element has the faces parallel and perpendicular to the shaft axis, then it's only going to be subjected to the shear stress, right? But if your element doesn't meet that criteria, meaning that the faces of that element is not perpendicular or parallel to the shaft axis, you are going to have a combination of shear stress and normal stress. Now, how can we find this normal stress? How can we find this normal stress? You of course have to have the angle your element makes, or the force you're applying makes the normal force to the surface. So the normal angle of each face with the axis of the shaft. For example, if that normal angle is 45 degrees, then we can find the normal forces using this analysis here. The normal forces is going to be equal to 2 tau max multiplied by A naught cosine of 45 degrees, which means that your normal forces are going to be equals to a square root of 2 tau max multiplied by A naught. And keep in mind that A naught here is the projection of the area on that element, right? So your sigma at the 45 degrees is the normal stress at the 45 on a 45 degrees element is going to be F. It can be calculated by dividing the force by area. So we're going to have tau max A naught divided by A naught square root of 2. The two areas are essentially the same area, right? So your sigma at 45 degrees is going to be equals to tau max, which means that you are going to have the maximum normal stress is if your element is at 45 degrees angle compared to the shaft axis. So for a face that has parallel and perpendicular faces to the shaft axis, we can say it is in pure shear. And for the other one, that is element C, that is at 45 degrees compared to the shaft axis, we can say that it has tensile stresses on two faces and compressive stresses on the other two. Okay. So what can we conclude from this analysis, right? Which means that you're going to have your maximum normal stress at a 45 degrees angle and your maximum shear stress at 0 or 90 degrees angle, right? It is going to help us in understanding the failure modes of the ductile and brittle materials. If you recall, the ductile materials are generally weak in shear, so they essentially fail in shear, right? But the brittle material are weaker in tension, so they usually fail in the direction of tension. So what does it mean when you are doing a twist, right? Which is it simply means that when you twist a ductile material, your failure is going to be looking like this because you have the maximum shear in this direction, right? And your brittle material is going to fail like this because you have the maximum tensile stress in the 45 degrees direction. Okay. Let's go back to the angle of twist. The angle of twist is related to your shear strain, of course. So based on this analysis, and in the elastic range, the shearing stress and shear stress are related by the Hooke's law. So your shearing stress is going to be equal to tau of max over G using the Hooke's law, which is Tc over Jg. How can we relate this to the angle of twist? You can essentially use this equation and this equation and rearrange and rewrite the equation, simplify to get to this final equation. So your angle of twist is finally related to your torque multiplied by the length of the shaft divided by the polar moment of inertia or polar second moment of area multiplied by G. But what's going to happen if you have a shaft with multiple radiuses, right? Which means that you're going to have multiple shafts. Your angle of twist is of course going to be the same, but you can calculate the angle of twist by the idea of superposition. So essentially analyzing each shaft separately. To give you an example, let's take a look at this statically indeterminate shaft. We are given the shaft dimensions and the applied torque. We would want to find the torque reactions at A and B, so TA and TB essentially. We have a hollow shaft at one side and we have a regular shaft at the other side. We are applying the torque in the middle, the torque of 90 pound-feet. And from the free body diagram, we can have this equation, and that's it. That's the only equation we can have. TA plus TB is going to be equal to 90 pound-foot. As we have mentioned earlier, to be able to find this statically indeterminate, to solve this statically indeterminate problems, we want to find the deformation, or we want to find the angle of twist, which tells you that the total angle of twist for your beam is going to be phi 1 plus phi b, right? The angle of twist of this one plus the angle of twist of this one, if you were to apply the torque separately, right? So if they were two separate shafts. So the angle of twist for the phi 1 for the case 1, which is the part A of the beam, is going to be TA L1 over J1G. The angle of twist in the other direction, in the other beam, is going in the other direction, so we have to subtract them because one is rotating in the angle of twist is in different direction, in the opposite direction, so you have to subtract the two, right? The angle of twist in the part B of the beam is TBL2 over J2G. So we have a relationship between the torque TB and TA, right? We have another relation. We have two unknowns and two equations. You can find the relationship pretty easily. Okay, so that's it for the theory. Essentially, the only equation you want to be aware of, the final equation is going to be this equation: phi is equal to TL over JG, right? Let's take a look at the experiment you want to do in this week. We are going to use the same base, same test setup. The only difference is going to be the supports here. We have these two supports, and you install the beam, the shaft right here. You apply the load here, and then you measure the angle of twist. Pretty simply. You can of course find the shear stress using TR over J. So that is the distribution of the shear stress. You can find the angle of twist using TL over GJ, and you can of course find the shear strain using phi R over L, the distribution. Keep in mind that for this specific beam, your polar moment of inertia is pi d to the fourth over 32, and d here is the diameter, right? And we can have the same stress strain plot we had for the normal stress and normal strain, for the shear stress and the shear strain as well. And that is going to be it. So essentially in the lab, what you are going to do is that you will be given different rods with different materials, different conditions. One of them will be a hollow rod, and you have to apply a set of loads to it. You have to measure the angle of twist, and eventually what you want to do is to find the shear modulus G. Let me actually write it down. The goal of the lab is to find shear modulus. Okay, and I will see you guys later this week in the lab. I will definitely come to the lab this time. And yeah, that's it for the lecture. Have a good weekend. And see you guys pretty soon.